So good afternoon everyone, my name is Samantha and today I'm presenting on my project titled Name Entity Recognition for Information Extraction. So this is the presentation overview which consists of 5 chapters, whereby I'll first introduce the project and its background. So firstly, what is feedback? So feedback is given by customers based on their own personal experience about a service or a product. It's important for both users and organizations as it can help to promote growth, improve performance, and increase customer satisfaction. There are currently plenty of organizations that rely on user feedback, and the Singapore Food Agency is one of them. For example, the SFA encourages the public to provide feedback about food establishments, whereby this feedback will be investigated accordingly. However, as organizations may receive a great deal of information, it's important to extract useful information in order to obtain a quick overview of the situation. Hence, an information extraction task known as the Name Entity Recognition was introduced for this purpose. The name entity task was developed to identify relevant information in a given text. The process of extracting these entities is formally known as name entity recognition. For example, given an input sentence, the NER will output name entities from a predefined category set. And a commonly used category set is the person, location, organization, and miscellaneous labels. Studies thus far have been applying NER models on the dataset itself to identify specific entities such as the food and location names. However, factors such as noise, data diversity, and data sparsity can influence the performance of the NER. For example, in Singapore, we have non-English food and location names such as Nasi Lemak and Kebun Baru, which may affect the performance of NER. In addition, data sparsity refers to the lack of training data to build the model. Hence, these factors may lead to the incorrect classification of data, resulting in lower accuracy. Thus, for this project, we propose the use of an NEM dictionary to improve the performance of the NER. So instead of applying NER models directly on the dataset is checked against the NEM dictionary for the identification of entities instead. So for example, given the food location NEM dictionary, as long as the entity is present in the dictionary, the chances that it will be identified correctly is higher than that of using the NER model on its own. So why is this important? So the use of an NEM dictionary can help streamline processes such as administrative tasks and feedback overview. In addition, as the NEM dictionary can help to extract name entities such as location names and addresses, this could further assist downstream tasks such as grouping of feedback based on location names. So although we're using the NEM dictionary instead of NER models to identify entities, the use of NER models are still required to generate our NEM dictionary. So the objective of this project is to conduct a study on NER models for building a Singapore food location NEM dictionary. This is done by first comparing the performance of different NER models on the benchmark dataset. However, due to unique food, street, and location names in Singapore, it was important for us to also conduct our experiments on Singapore-based datasets. Hence, we also apply the top-performing NER models to Singapore-based datasets and evaluate its effectiveness in extracting Singapore food location names and addresses. So now I'll be doing a brief run-through of the past-related works. So firstly, we have the conditional random fields, which is a sequence modeling algorithm that was widely used for NER. It's calculated using the probability function formula on the left, whereby the function refers to the probability of calculating label sequence Y given an input sequence X. Finally, we can also obtain the output label sequence with the highest probability using argmax. So in recent years, most NER approaches now use pre-trained transformers. These transformers rely on attention mechanisms such as self-attention, which considers other words in an input sequence when performing computations for a specific word. The attention function also calculates attention scores, so that more attention will be given to those words with higher scores during processing. So examples of transformer-based models that are closely related to this project is the BERT, XLMR, and Loop. We'll now take a quick look at the important features related to each transformer. So firstly, we have BERT, which was pre-trained on contextualized word representations using the book corpus and Wikipedia. It has two pre-training tasks known as the mass language modeling and the next sentence prediction. We also have the XLM model, which was pre-trained on the common crawl data. It was pre-trained using mass language modeling tasks without NSP, and also uses dynamic masking, whereby an input sentence is duplicated a few times, and a different masking pattern is used each time the sentence is passed into the model. Lastly, the Luke model was pre-trained to treat both words and entities within a text as independent tokens, allowing it to output the contextualized representations of both words and entities. Hence, its pre-training task is simply as an extension of BERT's MLM's task. So now I'll be talking about the models used for this project. So the third model was introduced to study the impact of using document-level features on its own. The study had evaluated the use of document-level features in various approaches for transformer-based models. They utilized FLAIR framework, which is an open-source natural language programming library, which allowed us to closely reproduce our experiment. So traditional NER approaches consider information within a sentence but not across sentences. So the purpose of using transformers is due to their natural ability to capture the features at document level with its self-attention mechanism. This is done by simply passing a sentence and its surrounding context through a transformer to obtain word embeddings. For example, the word Paris could be labeled more accurately as a location entity due to its right context, which mentions there is a city. The self-attention mechanism would then perform computations over all the input tokens, including the left and right sentences, enabling each token within a sentence to be influenced by its surrounding context. So the results obtained from the study showed that the use of document-level features and fine-tuning combined can help increase the performance of NER. With this conclusion, we chose to replicate the results of fine-tuning with document-level features for NER by utilizing the pre-trained XLMR large model as our transformer. So this model was trained with a single GPU, and the following are the hyperparameters used to train the model. Patience was used for early stopping, which enabled us to stop training if the results are not improving. So moving on to the next model used in this project. As document-level features can further improve the accuracy of NER models as seen in the previous study, the CLK model was proposed with the objective of further improving NER models with external context retrieval and cooperative learning. Like the previous model, it focuses on the use of document-level features. However, as document-level features require surrounding context as input, the CLKL model considers situations where such contexts are not available, such as in short comments and in search queries. Thus, this model was inspired by the practice of using search engines whenever we need more information. To facilitate better understanding, we break down the entire model into three main components. The first component is the external context retrieval process, whereby the Google search engine was used to retrieve a collection of semantically relevant text based on the input sentence. Next, we select a few top-ranking texts based on their semantic score against the original sentence. This is done through ranking the text from the search engine using BERT score, which is a language generation and evaluation metric. This helps to calculate the semantic score between input text and retrieved text. This score is calculated using concise similarity, and BERT score would then compute the recall, precision, and F1 scores accordingly. The retrieved texts are then re-ranked according to the F1 scores, with a large score indicating strong semantic relations between the input text and the retrieved text. For this experiment, we use the top 6 retrieved texts as external contexts, which are combined with the original input sentence. The following diagram shows the architecture of the entire external context retrieval process. The second main component in the architecture is the NER model. So although external contexts are helpful to various domains, it may not be desirable in time-critical situations. Hence, the NER model can accept 2 input views to cater to different scenarios. The original input view simply refers to an input sentence, while the retrieval-based input view refers to the input sentence and its external context. Luke was also used as the transformer-based embeddings model to obtain the token representations of the input. To recap, the Luke model enables the contextualized representations of both words and entities and is pre-trained on a large Wikipedia corpus. An additional CRF layer is also used for the prediction of named entities by computing the conditional probability of each input view. To find the most optimal parameters, we then compute the negative log likelihood loss during training. These are the respective loss functions for both input views. Lastly, to create a more unified model, since we have 2 different input views, cooperative learning was utilized. So the original study for this model had experimented between the use of 2 cooperative learning approaches, the CLL2 and the CLKL function. So the results obtained from the study showed that the use of CLKL had outperformed CLL2. Hence, for this experiment, we'll be utilizing the CLKL function during training. So the CLKL function focuses on minimizing the callback labeler divergence between output distributions of CRF. This helps to increase the likelihood of the two input views producing similar results, establishing a more unified model. The total loss during training is therefore the sum of the CLKL loss and the label losses of the CRF. This diagram shows the entire CLKL model architecture, which comprises of three main components: external context retrieval, the NUR model, and finally the use of the CLKL function. For model training, a single GPU was used, and the following are the hyperparameters used to train the CLKL model with and without external context. Details about the benchmark datasets used for the training this model will be discussed later. So moving on to our last model, we have the XLNet, which is an autoaggressive model that combines transformer XL mechanisms with the bidirectional capability of auto-encoding models like BERT. The results obtained from this study had shown how XLNet outperformed BERT on 3 tasks, such as reading comprehension and text classification. So traditional AR models are unidirectional, which means that they can only read context forward or backward, but not simultaneously. They are commonly used for generative NLP tasks, which require the generation of context in a forward direction only. However, AE models like BERT are known for its ability to model bidirectional context through the use of the masked language modeling task for pre-training. So as the MLM task works by predicting masked tokens with only non-masked tokens, this means that other masked tokens are not used for prediction. Hence, in order to help AR models obtain bidirectionality while solving the current limitations of MLM, a new pre-training task was introduced. So the permutation language modeling objective was proposed to help AR models obtain bidirectionality by permutation, which is a technique that requires pre-training on all possible word combinations within a sentence. For example, given this input as we try to predict X3, while training on all possible permutations of the input, we may have factorization orders such as the following. Assuming our model only sees context backwards, token X2 and X4 are used to predict X3 in the first order, while token X1 is used to predict X3 in the second order. Hence, we are eventually able to capture the context from all positions to predict a single token, modeling bidirectionality. This task can formally be defined as shown. The XLNet model also uses a two-stream self-attention architecture to enable target-aware representations. It comprises of two different types of self-attention. The content stream attention is simply the same self-attention layer in a standard transformer, whereby it considers both the context and position of all contents before the target token. However, the query stream attention is target position aware, whereby it considers the context of the first T-1 tokens, but only considers the target position at T. Lastly, the model also utilizes two mechanisms from the transformer XL. First is the relative positional encoding scheme, which was discussed in the previous slide, whereby the target position is captured and used as input to the query stream. Next, there is a recurrence mechanism that reuses the hidden states obtained from previous segments. This was done by simply caching previous content representations and then updating the attention for the next layer with memory. This can be expressed as shown. These are the hyperparameters used to train the model, and as XLNet requires much more computing memory, the maximum number of epochs the workstation was able to handle was only 4. Moving on to the next chapter on model evaluation. For this project, the English Cornell 2003 dataset was the benchmark dataset used to train the different models. It has a training, development, and a test file, and focuses on 4 types of name entities, which is the person, location, organization, and miscellaneous. And it was labeled with BIO tagging scheme, such that the prefix B represents the beginning of a new chunk, while prefix I refers to a tag inside a chunk, and prefix O refers to tags that are not recognized as name entities. We also use the publicly available benchmark dataset with external context for training the CLKL model. This table shows an overview of the benchmark dataset with and without external context for the CLKL model. Lastly, we also use Singapore-based datasets to test the prediction accuracy of the top-performing NR models. The Singapore newspaper dataset was crawled from Today Online, while the Singapore Hawker Centre dataset was taken from a one-stop portal. Only the hawker centre name and description fields were used for testing. We We evaluated the models based on precision we call F1 score. These metrics are based on the confusion matrix whereby TP refers to entities identified by the NER that also appears in the ground truth dataset. FP refers to entities that are identified by the NER that are not on the ground truth dataset. And Fn refers to entities that are in the ground truth dataset but not identified by the NER. With this, the precision we call an F1 score can be calculated as follows. We will now analyze the results obtained from this project. So based on experimental results for the benchmark dataset, the flat XLMR had outperformed all the other models in terms of precision we call an F1 score, while the CLKL with external context retrieval performed the second best. In addition, the CLKL without external context only fell behind second place by 0.35%. In accordance with our objective to build a location NEM dictionary, we then applied the top performing models on the Singapore datasets and evaluated their effectiveness in extracting location entities. So based on the results shown, once again, the flat XLMR model was the best performing model for the Singapore newspaper dataset. This could be because it was trained on a general news dataset, allowing it to naturally perform well on this dataset too. However, for the hawker center dataset, the flat model was outperformed slightly by the CLKL model without external context retrieval. The outputs showed that the CLKL model without external context retrieval was able to extract full Singapore addresses better than the other two models. For example, it could extract block 80 circuit road, while the others only extracted circuit road. In conclusion, the main objective of this project was to conduct a study on NER models for building a Singapore food location NEM dictionary. We had evaluated different NER models on the benchmark dataset, and results obtained showed that flat model had outperformed the others with an F1 score of 93.98%. Next, we also attempted to investigate further if the NER models trained on a general news dataset were still able to perform well on Singapore datasets. This was done by applying the top 3 NER models to the Singapore datasets. Finally, although the third model had outperformed CLKL without external context retrieval on both general and Singapore news datasets, we conclude that the CLKL model without external context retrieval was able to better meet our objective of extracting Singapore food locations and addresses based on its performance on our hawker center dataset. Hence, it's the best model to generate our NEM dictionary due to its ability to extract full Singapore addresses better than the other models. Thus, the correctly identified locations and addresses obtained from the CLKL model could be used to populate a Singapore food location NEM dictionary. To conclude this presentation, we list some possible future works. One possible future work is to have a fully labeled Singapore dataset based on the PIO tagging scheme. With this, future models could be trained on Singapore datasets too, which might increase the performance of NER. Next, future works could experiment with building a more domain-specific dictionary, such as the Singapore Food NEM Dictionary. Lastly, we experimented on the study of NER for NEM in this study without building the actual NEM dictionary. Hence, future works could build an NEM dictionary and further apply and test its performance on the actual application.